Hello. Today we're going to discuss the Intermediate Value Theorem, but in a slightly different way than we did a few weeks ago. Let's review some of the concepts of connected sets and uniform continuity. We'll need some of these today. Let's say that A and B are non-empty subsets of the real numbers. Then the following two statements are equivalent. First, the closure of A intersect B is equal to A intersect the closure of B equals the empty set. Second, A intersect B and the limit points of A intersect B and A intersect the limit points of B also equals the empty set. Any pair of non-empty subsets A and B satisfying either of these equivalent statements are said to be separated. Recall that A and B are disjoint if A intersect B is the empty set. So notice here that being separated is a stronger condition than being disjoint, since we also require conditions on the limit points of A and the limit points of B. The following result is related to separated sets. Say that S is a subset of the real numbers. The following three statements are equivalent. First, we cannot write S as the union of two separated sets A and B. Second, whenever P is between two numbers A and B in S, then P itself is in S. And third, for any non-empty subsets A and B satisfying S is the union of A and B, yet A intersect B is the empty set, there exists a Cauchy sequence consisting of A sub n's in our set A, whose limit P of the A sub n's is in B. Any subset S satisfying either of these equivalent statements is said to be connected. Otherwise, we'll say that S is disconnected. That is, we can write S as A union B for some separated sets A and B. Finally, we'll say that S is totally disconnected if, given two elements A and B in S, we can find separated sets capital A and capital B such that lowercase a is in capital A, lowercase b is in capital B, and S is the union of these two sets A and B. Let's go over a few examples. Any open interval I from A to B or any closed interval K from A to B is a connected set. The collection R of real numbers is also a connected set. Any disjoint union, say the closed set from 0 to 1 union the closed interval from 2 to 5, is a disconnected set. Here we can write S as the union A with B in terms of separated sets A, which is the closed interval from 0 to 1, and B, which is the closed interval from 2 to 5. The collection Q of rational numbers is totally disconnected. Here's why. Given two rational numbers A and B, we can find an irrational number Q between them. So this means we can write Q as A union B in terms of the separated sets, capital A, consisting of rational numbers X to the left of our irrational number Q, and capital B consisting of the rational numbers X to the right of our irrational number Q. The collection of irrational numbers is totally disconnected. Essentially, the proof is the same, but instead of looking at an irrational number Q, we look at a rational number Q. And finally, the Cantor set is a totally disconnected set. Now let's discuss some different concepts. Let's say that I is a closed interval. We'll say that a function f is Lipschitz if there exists a constant m such that in absolute value f of x minus f of p is less than m times x minus p for all x and p in our closed interval I. Every linear function is a Lipschitz function, and Lipschitz functions are continuous. Again, let's let I be a closed interval and f be any function. We'll say that f is uniformly continuous if, given every positive epsilon, any positive epsilon, there exists a positive delta such that f of x minus f of p is less than epsilon whenever x minus p is less than delta. We've seen the following four statements. First, every Lipschitz function is uniformly continuous. Second, if f is uniformly continuous, then f is a continuous function. Third, f is not uniformly continuous if and only if there exists a positive epsilon 0 and sequences in terms of a sub n and b sub n such that a sub n minus b sub n tends to 0, but f of a sub n minus f of b sub n is greater than or equal to epsilon 0 for any n. And finally, say that f is a continuous function on a compact set K. Then f is uniformly continuous. Now that we've reviewed all of this, we'd like to revisit what's called the Intermediate Value Theorem. Let's review what this theorem states. Given a closed interval I, let's let f be a continuous function. If L is a number between f of a and f of b, then there exists a point P in the closed interval such that f of p equals L. That is, f attains all of its intermediate values between f of a and f of b. Let's quickly go over the proof of this just to recall how this goes. Without loss of generality, let's say that f of a is less than f of b, and we'd like to consider the following set. This here would be the set of all elements x such that f of x is to the left of L. This is a non-empty set because we're assuming that f of a is less than f of b, so lowercase a is in this set S. In fact, because I is a bounded interval, S itself is a bounded set. This means that P, the supremum of S, exists. We're going to show that f of p is L by showing that f of p minus L is less than or equal to epsilon for any positive epsilon. Since our function f is continuous, this means that we can find a delta such that f of x minus f of p is less than epsilon whenever x minus p is less than delta. In particular, whenever x is between p minus delta and p plus delta, f of p is between f of x minus epsilon and f of x plus epsilon. Whenever x is to the left of p, then we know that x is an element of S. Since f of p is equal to the supremum of f of s, again remember that f is a continuous function, this means that we can find an x sub epsilon such that f of x sub epsilon plus epsilon must be greater than f of p, the supremum. But also f of x sub epsilon is less than or equal to L because we're assuming that x sub epsilon is to the left of p. The whole point here is that we're using the fact that the supremum of f of s is the point f of p. On the other hand, whenever x is to the right of p, we know that x is not an element of s. So this means that f of x is greater than L. So we see that whenever x is greater than p, f of x is greater than L, and therefore f of x minus epsilon is greater than L minus epsilon. However, as we just said, f of x, or x is greater than p, so we do see that f of x has to be less than or equal to f of p plus epsilon. Again, this is because we're looking at the supremum. Putting these together, we now see that L minus epsilon is less than f of p, is less than or equal to L plus epsilon. So this means that in absolute value, f of p minus L is less than or equal to epsilon for any positive epsilon, showing that, of course, f of p equals L. We're going to actually state now the intermediate value theorem in a completely different way. Here, we're going to look at how this is connected to connected sets. Let's say that S is indeed a connected set, and let's pick a function f that is continuous. We claim that the image, namely the collection of elements y, such that y equals f of s, for some x in S, is also a connected set. Let's explain why. Let's say that capital C and capital D are non-empty sets where f of s equals C union D, and the intersection of C with D is the empty set. According to our definitions, in order to show that f of s is connected, it suffices to construct a sequence of the lowercase c sub n's contained in our set capital C, whose limit L is actually in the other set capital D. To this end, let's consider the following pre-images. Capital A will be the set of elements x in S such that f of x is an element of C, and B will be the collection of elements x in S such that f of x is an element of D. Notice that capital A and capital B are non-empty. Indeed, capital C and capital D are non-empty, so this means that we can find a lowercase a such that C equals f of a is an element of capital C, and we can find an element lowercase b such that D equals f of b is an element of capital D. But of course, these elements lowercase a and lowercase b, by definition, must be in the sets capital A and capital B. Next, we claim that S is the union of A with B. Well, by definition, capital A and capital B are contained in S, so their union is also contained in S. Conversely now, we want to show that S is contained in the union A with B. So let's pick an element x in capital S. Then this means f of x has to be an element of f of S, which of course is the union of C with D. So then either f of x is an element of capital C or f of x is an element of capital D. But this either means that x is an element of capital A or x is an element of capital B. Finally, we claim that the intersection of A with B is the empty set. By way of contradiction, let's say that x is an element of the intersection of A with B. Then x has to be an element of capital A, so f of x has to be an element of capital C. Similarly, x is an element of capital B, such that f of x must be an element of capital D. But now this image, f of x, must be an element of both C and D. However, we assumed at the very beginning that the intersection of C with D is the empty set, so we find a contradiction. Now let's finish off the proof. By assumption, S is connected, so we can find a sequence A sub n contained in our set capital A, whose limit P is an element of capital B. Hence, we can define lowercase c sub n as the image f of A sub n as a sequence of elements in capital C. Now, our function f is continuous, so the limit, namely f of p, is the same thing as the limit of f of A sub n, which of course is the same as the limit of c sub n, must exist as an element of capital D. But this is exactly what we wanted to show, that this limit L is indeed an element of capital D. This completes our proof. Thanks very much for watching.